Hello and welcome to Lab to Launch, the new seminar series for researchers interested in pursuing entrepreneurship. I'm your host, Sarah Jane Murdoch, the Administrative Project Coordinator for the Institute for Innovation and Entrepreneurship at UT Dallas and the Operations Manager for the Venture Mentoring Service of North Texas. As we move through today's session, I invite you to post questions in the Q&A box for our guest speaker to answer. Our guest speaker today is Connie Manz, the co-founder and CEO of Qualia, Inc. She received her bachelor's and master's in material science and engineering from MIT. Connie has held various research positions at MIT, IBM in Singapore, and Draper Labs, and was a business strategy consultant with Mars & Company. After receiving a second master's at UTD with Professor Walter Voit, she transitioned to managing the $2 million+ budget and operations for the Advanced Polymer Research Lab and Center for Engineering Innovation at UTD. She joined Adaptive 3D Technologies, another UTD startup, in 2015 and has been with Qualia since 2016. Welcome, Connie.
Thank you, Sarah. So as Sarah mentioned, my name is Connie Manz. I'm CEO of Qualia, and I'm going to be speaking with you today on product development considerations. I'm going to use some examples from our particular company and our process of developing our products, and just to show different things that we took into account and had to, questions that came up when we were figuring out how to design our first products, and then after that, how to improve them. So first, a little bit about our company. We were formed in 2015 here in Dallas, and Qualia actually has a host of subsidiaries and affiliates that it is commercializing neuro and biotechnologies through. So we have Qualia as kind of the parent company, and then we have separate companies that are focused on specific markets and clinical applications. So while I say I'm CEO of Qualia, these are just a few of the different companies that we have at different stages of formation and product development. I'm going to be speaking primarily about Qualia Labs, which is focused on softening neural interface devices for non-human research applications. But at the end of the presentation, I'll touch a little bit on Qualia Oto, which is focused on the cochlear implant market, and Backstop Neural, which is focused on spinal cord stimulation. Our current team, you see here, it's a team of 8. We also have additional collaborators and medical advisors at each of the subsidiaries, but this is kind of the core team right now that's pushing forward Qualia. Before I go into our market, I wanted to explain a little bit of just basic definitions of what neuromodulation is and what neural interface devices are. So neuromodulation is the alteration of nerve activity through targeted delivery of stimulus to a specific neurological site in the body. We're focused primarily on stimulating through electrical stimulation. A neural interface is a device that actually interacts with the nervous system. So it can either stimulate, block, or record neural activity. And so this is the particular field or market that we've kind of entered. You can see on the right-hand side, 2 examples that you might be more familiar with of neuromodulation are cochlear implants, where you actually have electrodes that feed into the cochlea to help stimulate your auditory nerve. If you can't hear, it directly stimulates that. And then spinal cord stimulation, where you put electrodes along your spine and send electrical signals along your spine to help mask chronic pain that you might be experiencing. So in the research device field of neural interface devices, what I just shared with you was medical devices or human clinical applications. But with research applications, you also have a whole host of devices that have been around, kind of some more recently, some for decades now. And it's split up into a few different categories of devices. You have the ones shown offered by Neuronexus and BlackRock, which are silicon-based devices. So as you can imagine, silicon is a very stiff material. So while it's good for penetrating tissue, it's not the greatest in terms of biocompatibility and being constantly against tissue, because you have a large modulus mismatch between your material of your probe and your tissue. On the right-hand side, you can see some other devices like peripheral nerve cuffs and grids that are made out of softer silicone. With these devices, you have a modulus that's closer to the modulus of tissue, which is beneficial, but depending how thin it is, it's frequently hard to work with, just because if you have something thin and floppy that you have to surgically implant, it can get tricky. Additionally, with the cuffs, they're manufactured to certain diameters in certain circumferences. So how well it fits whatever nerve you're targeting, if you're wrapping it around a nerve, depends on how exactly you can match varying nerves of varying diameters. And so where our technology came in is we developed a process of photolithographically patterning electrodes onto proprietary shape memory polymers. We used standard microfabrication techniques that are found in semiconductor clean rooms to pattern these electrodes onto the polymers. And the benefit of the polymers is that they start out relatively stiff, not quite as stiff as silicon, but you can still see several orders of magnitude stiffer than brain tissue. But after you insert them, there's a temperature increase from room temperature to body temperature. And then in addition to that, they take up a little bit of water, and as a result, they soften so that they're closer to the stiffness of brain tissue. This helps to reduce tissue strain just from the modulus mismatch, as well as foreign body responses. When you stick something very stiff into the body, your body tries to protect itself, it forms a capsule around it or scar tissue around it, and what ends up happening is that you have electrodes that you can't record or stimulate from after a period of time because your body is trying to protect itself. So if you have these softer devices, that response is lessened. And also with the softening of the substrate, we can better conform to target nerves because you can kind of bend it and mold it to the exact shape of the nerve. So this was the technology that was first developed in Professor Walter Voit's lab at UT Dallas, the Advanced Polymer Research Lab. He was awarded a DARPA Young Faculty Award as well as a Director's Fellowship, which funded the early development of these devices. It funded the designs that you see here and just the distribution of these devices to collaborators at UTD and around the country and around the world. At some point in his lab, before Qualia spun out, he was sending about 1,000 devices out of his lab to different university research groups. And so at that point, it kind of made sense to ask, well, should we make a business out of this? And that's how Qualia was formed. So we benefited from having these early prototypes that were built at the university. But from there, there was kind of a whole host of other tasks that we kind of saw ahead of us for how we should choose our product and develop it and improve it after we kind of selected the initial products. And so a few of the things that the tasks that we focused on were, first and foremost, choosing the designs to commercialize, adding product support, improving the assembly and packaging of the devices, adding and improving features, and then exploring additional markets that the products could be expanded to. And so in kind of looking at each of these tasks that we kind of had ahead of us, we wanted to try to figure out a few different questions that arose. These weren't necessarily answered for every single situation, and different ones were prioritized at different times. But a few of the things that we thought about were, what is the user feedback? What do we have funding for? What are the team's skills? Can we outsource? And how will this affect pricing? So this is in no way an exhaustive list of everything that we needed to consider, but these were a few of the different things that kept popping up. And so, for example, when we were first selecting our designs, we had a whole bunch of different prototypes of all sorts of designs, and we had to figure out, well, which are the first ones we're going to commercialize. So obviously this relied a lot on the feedback of our alpha and beta users, all the collaborators that had been collaborating with the Voit lab. What I would caution is to use the customer feedback carefully. As we gained more and more feedback from different labs, and once we started commercializing and sending these to new customers, we realized that not all feedback is the same. The feedback that we received initially from collaborators actually sometimes also contradicted what we later heard from other customers. So for example, when we started developing our brain probe, a lot of the focus was making it as thin as possible. We had to figure out how thick it needed to be so that it didn't buckle when you were inserting it, but we also wanted to make it thin so that you could minimize the foreign body response and essentially make it to reduce how invasive it was. So this is kind of the approach we took at UTD and then early on in Qualia, making it as thin as possible, which ended up being around 35 microns thick. The issue we had with that was the early collaborators spent months and years working with these SMP-based devices, and so they got to know them very well and became very experienced with them. Once we started distributing it to new customers, we realized the feedback was kind of all over the board. Some people loved them, some people hated them, and ultimately we discovered a lot of it had to do with the fact that if you hadn't had any experience with devices like these, they could be very hard and challenging to work with. So depending on the surgeon's experience with different types of devices, it was either a great device or it was a terrible device. And so what we ended up doing was we ended up actually making our devices thicker, even though this kind of went against the early feedback that we received saying that thinner is better, it's less invasive. Making it thicker helped with making it bow less, bend less, and just made it easier to insert. So it increased the surgeon's ease of use. And so, yes, it's great to have a thin, non-invasive or less invasive device that reduces the foreign body response, but if no one knows how to implant it, no one's going to buy it. Another aspect of the feedback that we realized as we started distributing devices to more research groups was that sometimes the person buying the device was not actually the person using the device. Especially in some of the larger research groups, you would have the professor or principal investigator who's actually paying for the device. You have grad students and postdocs who are the ones that you're actually interacting with and talking about the devices with and are selecting the devices. But then you might also have a surgeon who's actually the one implanting the devices. And so it's useful to get feedback from all of them, but it helps to know what their role is to kind of tailor what kind of feedback you want from each person. One of the other aspects of design selection was what we had funding for. Each different design requires a different mask and can need a different development process based on kind of the assembly and the packaging. So for us, we had the advantage of SBIR funding, which helped to fund a lot of the initial design selection and product development. So I know a few of the other presenters have talked about SBIR and STTR grants before, but they really are great sources for funding development. There's the phase 1, which is focused primarily on feasibility and proof of concept and lasts for 6 months to 12 months and is up to $256K. And then you have the phase 2, which is longer, which is really when you do more substantial research and development towards commercialization of products. And so Qualia was awarded a phase 1 and then subsequently a phase 2 SBIR from DARPA, which was solely focused on commercializing these devices for research applications to provide additional research tools for the neuroscience community. So in that sense, we were able to kind of subsidize a lot of the fixed costs in developing these different designs. It gave us the flexibility in terms of funding to actually produce more of the different designs so that we could get those out to customers and get more feedback on which designs worked and what changes we needed to make. In terms of adding product support, one of the other things about feedback is that some of the feedback that you get won't necessarily require you to change your product. It might just be a matter of adding more support for your product. So it's very important to have good user guides, good customer support for your products, but at the same time, don't assume that the customers will read instructions. All of us know with a lot of the products that we buy, we get the instructions and we kind of just throw them to the side. And this is definitely something we realized with our devices as well. So we have very temperature sensitive devices. We run studies to see the proper ways to sterilize them. All that information was in our user guides, but even after all of that, we would get customers who would come back to us wondering why, after throwing devices into an autoclave and heating them up to 120°C, they didn't look so good and they didn't seem to work anymore. We also had customers who would receive the devices and had very basic questions of which is the top side and what's the bottom side. Some of that doesn't necessarily need to be addressed by changing the product, but you can show, hey, if you look under a microscope, you can look at this part of the image that has wording, make sure it's the right way. And some of it is just familiarity and talking to your customers the first time they use a new device. But it's not always about changing the product itself. Once we had our devices and we were sending them out to different labs, we started looking into improving the assembly and packaging of our devices. So with the nerve cuffs that we have, we typically assemble them with stainless steel wires using conductive epoxy and medical grade epoxy. We can add additional connectors on the back end of those depending on what the customer wants. With the brain probes, we actually designed a custom connector to go with those. So as you can see, the packaging as of right now, I wouldn't call it pretty, but it gets the job done, but can also be improved. So with all of these devices, you're putting them into animals depending on where the target nerve is. You have to get out of the body. The animals move around a lot, you get a lot of stretching, a lot of strain, and so a lot of times it's not actually the device itself that breaks, but it's the connections to the devices. And so we wanted to try to make the connections as robust as possible. We ended up actually taking several different courses in terms of how to improve the assembly and packaging. We actually did get a second phase 2 SBIR focused solely on the connectors and cabling for our devices, just because this actually ended up being one of the big issues in the whole neural interface community, just having better cabling and connectors. And so with the SBIR funding, that actually pushed forward the development of liquid crystal elastomer cables, like the one that you can see here. With the liquid crystal elastomer cables, though, while it was funded on the SBIR grant, this was actually something that was a little out of our skill set and expertise. So we actually submitted the proposal with UT Dallas as a subcontractor on it. We partnered with the Ware Lab. Dr. Taylor Ware had done some work previously at the Air Force Research Lab on liquid crystal polymers and liquid crystal elastomers. And this seemed like a good possible material for making new cables. I would say when you're looking at kind of any sort of product development, it's good to see whether or not you can consider using partnerships, subcontracts, or service agreements to expand your skill and your tool sets. It doesn't always make sense to just hire another person with another set of skills, because then you end up expanding your team very quickly, and frequently you don't need a full-time person working on some of these tasks. So partnerships and outsourcing ends up being a good way to go about expanding what your capabilities are. Additionally, I said service agreements as well because so we actually work very closely with various labs at UTD. We also use a lot of the facilities at UTD. So we have service agreements with the UT Dallas clean room and with various labs to use their equipment. And the benefit of that is that we don't have to spend hundreds of thousands of dollars on expensive equipment if we only need to run occasional tests. Instead, we can set up a service agreement with a lab and pay each time we have to conduct a test on their equipment. But that gives us kind of more tools that we can use as we develop our products without having to spend that money on capital. So while we had our grant pushing forward certain types of improvements for assembly and packaging, we also ended up taking another route. And I would say one other thing that I would add is that it's helpful to network and know the players in the market. So on one of my earlier slides, I had mentioned Microprobes for Life Science as a kind of as a competitor. They have commercially available products out in the research market. They've been around for several decades and are one of the established companies in the field. We actually ended up partnering with them. They have very good assembly skills, and then they saw the benefit of having our softening nerve cuffs. So we ended up working out a distribution agreement with them for distributing combination devices of our nerve cuff heads and their assembly. And in that way, we were able to provide additional products with improved packaging to our customers. This also helped us expand our customer base because essentially all of Microprobe's customers were now exposed to our devices as well. There are always kind of additional features that you can add to your products or features that you can improve on. A few more questions that came up as we looked at different things that we could do to improve our devices were whether or not the customers were willing to pay for the improvements and how much they would pay for them, but also whether or not the improvement was needed for the application or market. So you kind of have to weigh, at some point you have to be realistic about how much it's going to increase the cost of your device or your product and whether or not your customers are going to be willing to pay for it. So in terms of our devices, some of the features that we added fairly early on were different electrode materials and different connector options. We found that these kind of features were ones that the customers cared about. They wanted to be able to choose whether it was a gold electrode or a titanium nitride, iridium oxide, or platinum electrode. And for us, while it adds an extra process in the fabrication, changing out which materials we use wasn't a very difficult feature to add. Additionally, the customers were willing to pay more for different material if we chose different electrode materials that were more expensive. The same thing goes with the connector options. The market was very aware of the different connectors out there and how much they cost. So for example, if someone wanted, instead of just stainless steel wires attached to an Omnetics connector, if they can go and see that the connector is $50, they understand if we're charging $50 or $60 more to them as well and passing along that cost. With other improvements though, we found that they didn't actually make sense to do. Just because we could make the product better didn't mean we necessarily should. And so, for example, wireless devices and long-term stability of our devices. So our current polymer that we use on most of our devices starts to degrade if you leave it in the body for a long time. And so as it degrades, then the electrodes can't really record or stimulate anymore. We've shown that with the current formulation that we have, they're good up through at least 6 months. With a lot of research applications, 6 months is plenty. A lot of people do acute studies where the devices are only left in for days or weeks. Some do 1 month, 2 months. But in that sense, if you're trying to develop a new polymer, which we have, which would be stable for years or possibly decades, the added cost of doing that might not make sense if that's not what the products are going to be used for. In improving our devices, we did go down this route and make a new formulation and a new polymer, but all the components of it have to be made in-house. They're not commercially available, and so as a result, it can double the cost of a device or increase the material costs by an order of magnitude. And so while it didn't make sense necessarily to incorporate into all of our devices for the research applications, we have looked into other medical device markets that could justify further development of that polymer. So kind of on that front, to give you a feel for it, the research probe market is only about 2 million worldwide. Whereas if you start looking into medical device markets, those are much larger when you're talking about human clinical devices. So the cochlear implant market is about 2.7 billion right now, growing to 6.7. The central nervous system market, which includes spinal cord stimulation and deep brain stimulation, is about 5 billion now, growing to 14.5 billion in the next decade. And so when you're looking at markets that are this large, and you're looking at what the devices need requirement-wise, if you're talking about a spinal cord stimulator or a cochlear implant, you really do want to implant it once and not have to worry about it for years or decades. And so you need a material that's going to stand up to that. Additionally, the cost of these devices is so high that the material development costs and the additional material costs that we're passing along aren't nearly as substantial. For the research probe market, your probes are costing maybe a few $100s up to $1,000. When you're talking about cochlear implant, it's $30,000 to $50,000 for a surgery, including the implant. And so clearly, there's a lot more that the cost, because it is so much more expensive, adding the additional cost for the material development is not insignificant, but it's a much lower factor or less important factor. And so the last point I wanted to talk about was kind of expanding into other markets. I've kind of talked about how we had this core technology that we were using for the research device market, but the core technology has a lot of promises for medical devices. And with neuromodulation, that is ultimately the goal, to use these devices in humans to address different clinical indications. So two of the ones I mentioned that are more established are cochlear implants and spinal cord stimulation. So we actually did look at kind of what do the electrodes look like right now, and can our technology provide advantages? And so right now, cochlear implant electrodes are, if not entirely handmade, a good portion of the process is still made by hand. There is about 16 to 24 platinum or platinum iridium electrodes that are coated in silicone. And this is kind of how all the electrodes look right now. They can be pre-curled or they can be straight and curl as you push them into the cochlea. So given this is kind of what the current electrode arrays look like, we kind of asked ourselves, can we improve on that with our technology? And so Qualia Oto is now pushing forward the development of a thin film cochlear implant. The idea being, with the thin film photolithically patterned electrodes, we can increase the number of electrodes on the arrays, which will improve specificity. With the smaller electrodes that are more well positioned in the cochlea, you can reduce the current consumption, leading to either a longer battery life or a smaller battery. And by making the implants smaller and thinner, you'll reduce the insertion trauma. Because of the way that we manufacture them too, there is the potential to have additional customization further down the road. We've done the same thing with the spinal cord stimulation market. where we've looked at kind of what is the current state of art for the leads. And so again, you get platinum iridium electrodes surrounded by silicone or polyurethane. They come in kind of two main shapes, either they're cylindrical leads or they're paddle leads that are flatter and wider. All of these, though, are approximately 1.3 to 1.4 millimeters thick. You also get a lot of complications from these leads migrating or breaking after implantation. And so Jason Carmel is a collaborator who was at Cornell, now he's at Columbia, and he's focused on motor recovery in spinal cord paired stimulation for motor recovery. And so early on, he actually received some of the kind of early prototype devices for spinal cord stimulation in rats. He was using these for cervical spinal cord stimulation in the rats for motor recovery. And he realized, hey, these devices are really great. They actually conform to the spinal cord and they don't move around after they conform. And so why don't we see whether or not we can use this in humans? And so Backstop Neural's focus has been to kind of translate these first prototypes and products that were used in rats to a human-sized device and a human-sized lead that would be significantly thinner. I mean, we can pattern devices 35 microns, 50 microns thick, but we can also make them thicker. So if you had something, say, 0.5 millimeter, it's still less than half the thickness of the current devices out there. If it can, you can put it in the epidural space and have it heat up and soften so that it conforms to the spinal cord, then you get a lot less lead migration, and it also conforms and you get increased contact and better stimulation as well. And so that is kind of how we've taken the technology and translated it to a different medical device application. A few other considerations I wanted to touch on, product related, but also just kind of broader as well. I talked about all the grant funding that we received to help with the product development. But before applying to grants, make sure that you have kind of all the requirements that you need to apply. Some of this takes time. So forming the company, having the bank account, getting a Dun & Bradstreet DUNS number, and requesting a cage code. Each of these takes time. And so you don't want to come up against the deadline of a grant and realize you can't apply just because you didn't have all these kind of administrative aspects in place. Intellectual property. All of our kind of core technology was developed at UTD, and because of that, we had to license the technology out of the university. I would say if you're kind of in a similar situation where you've developed something with the university, start the process of licensing early, depending how complicated your situation is. And as you can see with Qualia and all its subsidiaries, it was a bit more complicated. It can take time to figure out all the licensing details. Aside from IP, or from patents at least, you should also make sure you just have a broader IP strategy. Not everything needs to be patented. You can rely on trade secrets for a lot of things as well. And with university research, that may be the route you have to take just if things have been disclosed in publications before. But either way, you do want to have a strategy for how you're going to protect your IP around your products. And the last point that I did touch on in different bits was that you should build your team slowly. With startups, I think most people do expect to wear multiple hats. Partly this is just because when you're small and growing, there's a lot of different roles that and tasks that need to be handled, but they don't take someone's full time. Salaries are fixed costs unless you have a lot of hourly employees. And so it doesn't always make sense to say, well, I'll hire someone to take care of that. I'll hire someone to take care of that. Then you end up with a very large team with people that might be twiddling their thumbs if they can't do other things. And so it helps to have people that can kind of manage multiple tasks within both product development, but also the other sides of the business. So with that, I'll see if there's any questions.
We do have some questions. So first question is from Dresden. What resources are available at UTD to help with product development?
So I touched on this a little bit, but there's kind of a whole host of different ways that I've found that UTD works with us. So we actually license space from the Venture Development Center. So that's office space and lab space, which you kind of need to develop your products. We have a lot of lab service agreements, as I mentioned. The UTD clean room is actually where we fabricate a lot of our devices. And so that's kind of a straight fee for the number of hours we spend using the equipment there. But the UTD clean room is a multi-million-dollar facility. So not having to set up our own clean room clearly saved us a lot of money. In addition to that, as I mentioned, other pieces of equipment are available through specific labs, through lab service agreements. So we have agreements that have just given us access to different testing equipment so that we could test our polymers, test our final devices. Sometimes it's a backup. If some of our equipment breaks, there's another piece of equipment we can go to and use for a fee, but just having that available is useful. Through our grants, we had subcontracts with the university. So actually setting up sponsored research agreements with the university is a good way to have additional people with additional skill sets working on your projects. And so that's provided ways to expand kind of on what technologies we can incorporate into our products. Aside from that, I would say also, I guess, the human resource pool as well. So we've had several part-time workers. We've posted jobs on Comet Careers to get part-time workers to help with assembly and testing. And some of these have become full-time employees with us. And so kind of from the equipment to the human labor to just joint partnerships and collaborations, UTD has definitely provided a lot of support for developing our products.
Yeah, that's fantastic. Trey has a question. Where are you getting your market data? For example, you mentioned your cochlear implants.
So it's kind of a mix. We do have market research reports that we've purchased now. So some of the cochlear implant data and the other market data that are presented here was from that. You can usually just do a Google search and find basic numbers for markets, but when you want to start getting into a lot more, then the market research reports tend to be expensive. They're generally around $5,000 a piece, so it is kind of a significant cost, but when you get to that point, sometimes it is necessary. Aside from that, though, if you know the main players in your market, you can figure out quite a bit, especially if they're public, just by looking up their annual company reports, figuring out what their sales and revenues are, and if you can find information on what market shares they have. It's a lot of digging and a lot of searching, but you can piece together information in that manner too, if you can't afford to actually buy a market research report.
Another question is, what's the best way to identify and reach out to potential partners in the field and market and navigating those agreements?
So we kind of benefited from the fact that Dr. Voit, who's president of our company, knew a lot of the people just from his research and attending conferences. I would say conferences are a great way to start. Any conferences that kind of are important to your field, everyone who's big will have someone there. And just in terms of networking there, going to different presentations, trying to talk to them afterwards, that's a good way to start some of the conversations. beyond that, I mean, we've had people that just reach out to us, find our contact info and email us. So that is always an option as well, where you can do that with other companies. And sometimes that does lead to good collaborations. If nothing else, it frequently starts discussions. If it doesn't always have to be with someone who is really high up in the company. Sometimes partnerships can start up with particular research groups within the company first before it actually moves higher up.
Cool. We have about 5 minutes left. We do have a few more questions. Our next question is, so after the SBIR, STTR grant funds, what are other best ways for further attracting funds for development?
Let's see. So hopefully the goal of a lot of SBIRs and STTRs actually after phase 2 is to be somewhat self-sufficient with the commercialization of products. Clearly that's not always the case, in which case then you're going to have to go down that route of fundraising. And I think Brian Chambers spoke on that quite a bit from the VC side. There's the VC option, there's the angel investors option. I know UTD kind of has networks or has different networks that they can connect you with, right? But beyond SBIR grants, you can either get more SBIR grants, but if it's for the same type of technology, at some point you're going to hit a wall where it needs to be developed with outside funding.
Trey had a follow-up question about the market research reports. Do you know, could you like say where you buy yours?
So we've tried a few different ones. A lot of if you Google market research reports, you get a lot of random companies that seem to sell the same type of report. We have tried one of those before. We've also had a subscription before with Frost & Sullivan. Right now we use ID TechX. And so we've kind of bounced around as well, partly because I'm trying out different vendors, seeing which one actually has the type of market reports and the type of research that I like. So it might be a little bit of a trial and error, but those are the ones that we've tried.
Would you consider working with researchers at other UT schools to co-develop products?
Yes, I guess would be the short answer. We do a lot of collaboration with universities, and so a lot of the co-development, I touched upon it a little bit. A lot of it was UTD sending devices to other collaborators. So a lot of those collaborators are actually now involved in the Qualia family of companies. So I didn't introduce him, but Ken Lee works at UT Southwestern, and so he is a co-founder on our cochlear implant company. Jason Carmel works at now Columbia, formerly Cornell, and he actually is a co-founder for Backstop Neural. So we have a lot of different collaborators, not just in UT system, but elsewhere. And we're definitely open with UT system as well. Within the university, UT Dallas itself, we've worked with Stuart Kogan, we've worked with Joe Pancrazio, Eric Kildebeck, Dr. Romero used some of our early devices. Dr. Ware was our subcontractor. So clearly we're up for collaborating.
Yeah, I love to hear that. Let's see. Our next question is, can you compare your company with Neurallink?
Neurallink. I'm trying to think. Is Neuralink Elon Musk?
Not sure. I'm sorry. It was an anonymous question, so maybe they'll.
Give me one moment. Is it okay if I stop sharing for a second?
Yeah, no problem.
Yeah. So, I'm sorry, for some reason I'm blanking on them. Okay, so yes, Neuralink is Elon Musk's company. It's hard to compare because Elon Musk has a lot of money and we don't. I think Elon Musk is very focused on brain-machine interfaces, and so his goal is very high channel count devices to kind of be able to record from a lot of neurons in the brain. I'm a little bit envious of his the capabilities he has. He's kind of vertically integrated and has everything. My impression is that he has everything that he needs. We've had to rely a lot on collaborators, but he has the animal research, the fabrication facilities, the assembly, everything. He has the funding to support all of that in one. I would say, it's hard to compare because we have specific markets that we're targeting that don't fully overlap with what Neuralink's goal is. We have the research device market, which is not really anything that Neuralink is interested in. And then we're going after targeted kind of neuromodulation for clinical indications. So how to treat spinal cord injury, or how to treat deafness, or how to treat respiratory illnesses with stimulation. Whereas my impression, at least, of Neuralink is that it's really focused on kind of the integration of neuromodulation and with the brain.
Yeah, that makes sense. We are out of time, so thank you so much for sharing your time, talent, and resources, Connie. We really appreciate it.
You're very welcome. Thank you.
So please join us. Our last session will be 2 weeks from today. We're going to be welcoming a panel of industry experts to discuss technology commercialization in Texas during the next Lab to Launch session. So please see the announcement in the Q&A section for the link to view the complete series schedule and to register. Have a great afternoon, everyone.